بسم الله الرحمن الرحيم. هناخذ تطبيق مهم جدا بالنسبة للدكاترة أو الطاقم الطبي. هنطبق واحد من الأمثلة. المثال هذا تلقوه في صفحة 327 اللي هو المثال example 9.6 وهذه مهمة جدا. فيه patient بينقلوا له دم يبدو ارتفاع الاتش هذه ارتفاع الشجرة هذه بحيث انه تمشي بالجرافيتي بالجاذبية. اوكي. an IV intravenous injection is a type of gravity assist. We'll say consider that the hospital patient who receives an IV under gravity. Under gravity is that it drops with the gravity only. Okay, and gravity flow, of course, they say it's in the figure. If the blood gauge pressure in the vein, blood pressure in the vein is 20 millimeter mercury. Above what height should the bottle be placed for the IV blood transfusion to function properly? اوكي. بالترجمه ان نبي ننقل دم للمريض، فنبي نحط شكاره الدم على ارتفاع كم بحيث انها تكون يصل الدم يدخل الدم في العروق نتاع الفينز نتاع البيشنت. طبعا من هنا نلقى ان ضروري ان الضغط هنا يكون اكبر من الضغط نتاع الفين بحيث انه يخف. لو انه اقل الدم حيطلع بالعكس. لذلك ضروري نعرف ان نعمل ضغط اكبر من الضغط الدم اللي في العروق بحيث انه يدخل للمريض. فبسيطه جدا العمليه كلها. اول مره تحويل، هذا بس تحويل. هذه كل 20 مليمتر زئبق اللي هي 133 بار لكل مليمتر زئبق، لأن حنحول مليمتر زئبق مع الحل مليمتر زئبق. هذه حتعطيني 2.66 times 10 to power 3 PA. Okay. The pressure should be greater than the pressure in vein, and the pressure is rho GH, rho of the blood, rho of the whole blood. The rho of the whole blood is, this is the blood, is 1.05. It's in the front, in the list 10 to power 3 kilograms per meter cube. This is the mass of our volume. Then H is PV, which is, we say, greater than this here, greater than PV over rho G, which is 2.66 times 10 to power 3 over 1.05 times 10 to power 3. Gravity is 9.80. Okay. That will be 259 of meter, which is about 26 centimeter. Then we should put here 26 centimeter in order to the blood flow into the patient body. Very simple equation, okay, and very important for that. Okay. I also yesterday gave the Archimedes principle. Okay. And here we find on the end of fluid we have this body. Okay. Merged here. Okay. We have here the mg. We have here the pressure P1, and here P2. Okay. And we have here also the FB. FB is equal to mf of G. Okay, which is rho F G VF. Okay. We say that the water displayed, okay, the water displayed is the same mass, the mass of the liquid displaced is the same the mass of the merged body. You have in very clear in figure 9.4. But the point force in example 9.7. Please go for example 0.7, follow up the steps and apply for the law. Just use all the equations. Okay, but because we have to get to a new subject. Which is the specific gravity. Specific gravity. Which is any gravity, rho of the solid or so is for the water. And this is here, of course, unitless. Okay, the specific gravity, this is called specific gravity. The rho for the solid, okay, the substance, this is density of substance. Okay, also in because that if you have very small numbers You don't have to use the SI units, which is kilogram, meter, second. We use the CGS, centimeter, gram, second. This is for the small changes, because kilogram is big quantity, meter is long quantity, and but the time second is okay. We have to use this PS in gram per centimeter cube, which is the CGS system. Okay. Now we'll start in the fluid dynamics. Fluid dynamics and Bernoulli's equation. Okay. This page 3 in your book. The flow. What's the flow here? We have here flow like that, and we have this kind of flow, and we have this kind of flow. Okay. This, of course, will be in V1 velocity, and this is V2. Of course, not the same velocity. We call as the fluid here is ideal fluid. What's the ideal fluid? You have 4 conditions for the fluid to be ideal. Steady, first, irrotational, non-viscous, incompressible. The 4 conditions for the fluid to be ideal. The steady flow means that all the particles of fluid have the same velocity as they pass a given point. All of them. They have the same velocity while crossing a certain point. And condition number 2, irrotational flow, means that a fluid element or a smaller volume of the fluid has no net angular velocity. We know that. If the velocity like that, we don't have angular velocity, such that will be rotating or so, or make some currents. This condition eliminates the possibility of wire pools and eddy currents. They will not make like eddy currents like that. Okay? It will just flow straight. This is condition number 2. Condition number 3, non-viscous flow means that viscosity is negligible. Then we neglect we neglect the viscosity. We suppose that this fluid has no viscosity. Viscosity is internal friction. That makes the fluid viscous. There are friction between the has with the particles or elements inside, which resist the flow. When the fluid wants to flow, if there's friction, that will make the movement slower than normal. Condition number 4, incompressible. Incompressible means that the fluid density is constant. Okay, is constant. Because if we is compressible, then we'll find different viscosity in the same fluid. Okay. Equation of continuity. This is very important also. Equation. Let's start it like that. Delta M1, part of fluid. Let's make the drawing here. Okay. Like this. Okay, and we have here this fluid here. I'll make colors just to make it clear. Okay, we have part of the fluid. Let's say call this is delta M, and we give it 1. And we have here force. This is area A1, and here is A2. F1 is equal to, okay, this is F1 is equal to P1 A1, as we know before. And this will move with velocity V1, and this here is delta x1. We say this is x here. Okay? And we say that delta x1, as we've taken before in mechanics, v1 delta t. Okay, and here this is y1 up to here, y1, and this here y2. Okay. Let's see. Delta M1 is rho 1 delta V1. We say that M is equal to rho V. From rho is equal to M over V, volume. This is volume here. Okay? When we write this, this is volume. But if we write this, this is velocity. Okay. Okay. Delta M1 is rho 1 delta or change in volume 1. And this will give us rho 1, and the volume here is delta, we'll say, okay, we put the area 1 delta x1. This is the volume. We have x and we have area. Like we say the volume of any cylinder, we say this is the length and this is the area. Okay, this is the area, and the volume is area times h. In this case, we have the area, and h is x, the length of this. Okay, as our cylinder is like that. Okay, this is the x, and this is the area. The volume is a delta x. Okay, and x we say is v1 delta t, then is equal to rho 1 a1 v1 delta t. Okay, the same as we if we consider that the volume, the A2 here, delta A2, okay, this is delta M2, and we have A2 and so on. We'll apply the same thing as we applied for delta M1, delta M2 rho delta V2, rho 2, and that will give us rho 2 A2 V2 delta T. Okay. We have, you know, the delta M1 is the same delta M2. In this case, we have delta M1 is equal to delta M2. Then, we'll see that delta M1 is rho 1 A1 V1 is equal to we see here the delta T, okay, in the same time, okay, in rho 2 A2 V2. That tells us is the rho A. V is constant. Okay. Now we have, it's the same fluid. Then is rho 1 the same as rho 2? We'll take it out. Okay. Delta T is the same. Okay, we'll say delta T in this case here, and rho 1 is the same, rho 2, the same fluid, the same density. Then we have that A1 V1 is equal to A2 V2. Okay, this is equation of continuity for an uncompressible fluid. AV also is constant. From this, we say, if we want that the V2 here, V2 is equal to A1 over A2 V1. The figure 19 explain the things when you use that narrowing or reducing the area or cross-sectional area. You'll find that the fluid goes faster than the wide one. Then the velocity proportional to 1 over A. What's that? If A is big, okay, wide or so, the velocity is low. The other way around. Okay, let's make some example for the blood. Okay, since we are talking to the future doctors in the future, okay, medical schools, blood flow and cholesterol or bloco. We have, for example, here, this is the vein, okay, and we have cholesterol, here, and the blood, that's supposed to go like that, while the cholesterol is narrowing here and then goes again here. The cholesterol, just like when we say for the engineers, the pipe has some damage or so. The cholesterol, okay, the blood is going here. The cholesterol inside the vein will narrow this area, okay, and we know that what will happen for V1 and V2, because this is A1 and this is A2, and back to A1 as well. We'll see what's the cholesterol here. Make the pressure and the veins. Okay, and we'll apply for very simple equations. It's not complicated, and you have to remember this while you are. We call this black hole. Cholesterol black hole. Okay, cholesterol. Cholesterol black hole. High cholesterol in the blood can cause fatty deposits. Then this is fatty deposits. Called black hole to form on the wall of the blood vessel. On the wall of the blood vessel. Suppose a black hole reduces the effective radius of an artery by 25%. and here reduced, okay, reduced with 25%. How does this partial blockage affect the speed of blood through the artery? الكوليسترول صغر الفتحة نتاع أو الشريان إلى في نسبة 25%. يبي سرعة الدم في العروق. Okay. Now he came to the continuity equation of continuity. This is called equation of continuity. Okay, A2 V2. Okay, what's given that R2, and this is here because it's circular. This is R1, and this is here R2. Is equal to 75 of R1. The R1 is 100%. We reduce that, we reduce of this 125% remains 75% of the volume, of the area of that, or radius. Then that will be, this is R1, and this will be reduced, okay, reduced with 25%. Okay, reduced 25%. That means what we have here, this 25%, then this here, 75%. Which is this one here. Okay, R2 is 75% of R1. Okay, that V2, we need to see V2 is equal to A1, A2, R1, sorry, V1 of the velocity V1. A is pi R square. Okay? V2 is equal to pi R1 square, and here pi R2 square. V1. And that, we said R2 is 75% of R1. Then here pi times 0.75 of R1 square, all square, this is all square, over by R2, by R2 square. Okay, this will be calculated like he said that R1 2 R2 is 1.1 over 175, and the V2 is, okay, pi goes with the pi and so on. That will be 1 over 0.75, of course, square V1, which is 1.8 V1. What's 1.8 V1? The 1 is 100%, plus is 80% V2 is 80% plus increased 80% of V1. That means if we have, for example, 10 meter per second, V1, okay, that one will be V2 is equal 1.8 times 10 is equal to 18 meter per second. That's what we call the 80%. Okay, you solve at home 9, example 9/12. Please work hard and use the simple equations. Bernoulli, okay? Yes, guy? Bernoulli. He has equation, then we call it Bernoulli equation. Okay? S for, that's his equation, for example. Okay. He used the work or network, okay? And network we taken before is that the kinetic energy, change in kinetic energy plus the change of potential energy. Okay? The work here is the work is force times x, and then the force here is ma x. Okay? And we use all this, then this here, delta P, delta M over rho, and the pressure 1 minus pressure 2. What equals this here? Half delta M V2 square minus V1 square. Okay, change. If we say this is the change on in the kinetic energy. The same here we have mg y2 minus y1. I remind you with the k is equal to half mv square and u is mg y. Okay, and this here is delta y, and this here delta p. We'll see that delta m goes with the delta m goes with the delta m, and multiply by rho. That gives you P1 minus P2 is equal to half rho times V2 square minus V1 square minus rho G Y2 minus Y1. Let's solve for this. This here half of rho V2 square minus half of rho V1 square. Okay, we have here that, I mean this is plus, okay. Rho G Y2 minus rho G Y1. let's take the case, the first case and the last case. What we have here, this goes in this here, and the one it has the one goes to the one here. Okay, now P1 plus half rho V1 square plus rho G Y1 is equal to P2 plus half of rho V2 square plus rho G Y2. Okay, this equation is 918. Okay, which is called the Bernoulli equation. It's very simple how to get this equation from the equations we have taken before, as network is delta K, or change in kinetic energy, plus the change in potential energy. Okay? When we say that P1 plus half of rho V1 square plus rho G Y1 is equal to the same thing if in the case number 2 is P2 plus half rho V2 square plus rho G Y2. That means that everything we say that pressure plus half rho V plus rho G Y is constant. Okay? Okay, Bernoulli equation or principle can be applied to many situations. For example, for a liquid at rest. Liquid at rest. What does it mean? V is equal to 0. Okay? If this is 0 and this, okay, if this is 0, okay, this 0, and we'll take P this side, then P2, or this side here, P2 minus P1 is equal to rho G Y1 minus Y2. Okay, just try it here. You try this. Now this is okay. P1 plus rho G Y1 is equal to P2 plus rho G Y2. Okay? We said we'll subtract this here. Then this is P2, and this is go with minus. Okay? What we have here? This is the first rho G Y1, and this is with minus rho G Y2, which is rho G Y1 minus Y2. Okay? And this is P2 minus P1. Okay, let's make that the area, change in area, and in velocity. And we have here this tube. Okay, this tube here. It's narrowed here, and we have an open here, opening here, okay, and we have another one here, and we have another one here. And we'll see the flow like that. When it comes here, it comes like this. And then back to okay. And so on. This here, this is A1, V1, and this here, A2, of course V2, and we have here the same A1, V1, and so on. In this case here, we have pressure, high pressure. Here, low pressure. And here is high pressure. In the engineering, we say that the airplane wing is this way, like that, and it goes like this. Here we have V1, and we have here V2. Okay? V2 is greater than V1. Then P2 is less than P1. And this is P1. And this here, P2. Okay? P1 is greater than P2, then the plane goes up. The plane goes up. Just remember that we have the Bernoulli equation, we said. Let's apply for we have an example 913. To save time, because we run out of time, I have to give you the hints to solve every example. Otherwise, it takes us a long time. Flow rate from a tank, Bernoulli equation. You see the tank here is opened, okay, and has a hole, small hole in the middle, which is below the fluid surface with y2 minus y1. The level of the fluid is y2, all from the surface of the fluid until the base of the container is y2. The level, the height of this hole from the base of the container is y1, and between the surface of the fluid until this small hole is y2, of course, minus y1. Okay? And now we have the equation is A1 V1 is equal to A2 V2 is the flow rate equation, where AV has a unit of course, meter cube per second. Meter cube per second. This is very important. The flow rate is AV square. SAV, A1 V1 and A2 V2. That will be meter square for A multiplied by meter over second. Okay, that will give you the m3 cube under for second. Okay, given a specific value, the values are given, so samples will be used. Because they don't give you any figures, then he will use only samples, like V1, V2, A1, A2, P1, P2. He doesn't give you values. Then use the same figures. Like here, Bernoulli equation, P1 plus half of rho V1 square plus, we have the equation, Bernoulli equation, okay? And also we came to the V1 square. The pressure is the same. Why the pressure is the same? Because it's open. It's open to the air, and we have only the pressure of the air. Here we say we can use note that y2 minus 1 is just the height of the surface until up to the hole, above the hole. The atmospheric pressure acting on the open surface, okay, and at the hole P1 and P2 respectively, okay. Then the atmospheric pressure, okay, acting on the top open surface and at the hole, okay, respectively, are essentially equal, okay, equal and cancel, because we don't have any pressure from outside or any force. You have just the atmospheric pressure. Then P1 and P2 are the same. Came out with V1 square, it's okay, as does the density, the same fluid. It's the density the same, okay. And then what we have only, let me write here Bernoulli equation, is P1 plus half rho V1 square plus rho G Y1 is equal to P2 plus half rho V2 square plus rho G Y2. We say the pressure is the same, it's atmospheric pressure. We found that also the density is the same, okay. And we have here, for example, multiply, this is, we have the half V1 square plus GY1 is equal to half of V2 square plus GY2, okay. Let's multiply all by 2 because, or let me do it like this. Take the V together, half of V1 square minus V2 square is equal to GY2 minus Y1, and multiply by 2, V1 square minus V2 square is equal to GY2 minus Y1, and we have this here, we have figure here, and we can say that we have also the areas like A1, V1 is equal to A2, V2, okay. Okay, now this is the cross-sectional areas. V1 from this here, V1 square, he used only the V1, which is the flow rate of the tank A1 tank. They used here, they said, if the surface is big compared to this open here, okay, V2, for example, or V1 here, V1, V2 is moving very slow, approximately zero, approximate to zero, because it's a big surface. The movement or the velocity of the surface is slow, approaching zero. Okay, then we have only, since this here 0, then V1 is equal to V1 square is equal to GY2 minus Y1, or V1 is equal to square root of 2G Y2 minus Y1, as you see here. Okay.